We can start 10 seconds early. That's okay.
Sure.
Okay. So welcome back for the final talk of today. It's my pleasure to introduce Sifan. Sifan Yu, who was actually at my talk in Singapore last month, but I'm too scary apparently.
No, you were too handsome.
So he's going to be speaking about low regularity local well-posedness for the elastic wave system. Thank you very much.
Thanks, Sam, for the nice introduction, and thank organizers for hosting this beautiful conference. And it's a great pleasure to give a talk here. So today I want to talk about low regularity local well-posedness for elastic wave system. An appropriate subtitle that fits the vibe of this conference should be how to avoid ill-posedness driven by the instantaneous shock formation for some multi-speed wave system in the regularity region. So let me do the opposite and show you my main theorem at the very start. And the rest of the talk will be devoted to make sense this main theorem. So I consider a very special elastic material, which we call the admissible harmonic, in 3 space dimensions without any symmetry assumptions. So we split dynamics into the divergence part, which I denote by phi, and the curl part, which I denote by psi. I choose different pronunciation, just avoid confusion. So phi, the divergence part corresponding to the physical phenomena of the pressure wave, the longitudinal pressure wave, and psi corresponding to the shear wave. Okay, so the first assumption is that the divergence part leaving H3 plus. So ideally, this n is H3 plus epsilon for any small epsilon. That's the sharp result I want to get. And psi, the curl part, lives in 1 degree higher, okay, initially. And of course, you need to add an assumption so that your system is hyperbolic at the very beginning, and you can preserve the hyperbolicity for a short while because we are doing a local problem. So once you have these 2 assumptions, the result is that the Sobolev regularity for both parts can be propagated, okay, at least for a short time. And moreover, the 2 parts satisfy the following Strickart estimates in the L2 norm in time and L infinity norm in X. So as I said, the rest of the talk will be devoted to make sense this main theorem. So the talk is based on the joint work with my colleagues in Singapore, so Anxin Liang and Chen Haoyang. So, so the plan, half of the talk will be devoted to introduce you all kinds of the elastic wave equations. So the special thing about the elastic wave equations is that it highly depends on the material that you choose. So I hope this can serve as an invitation for you to pick up your favorite material so that you can implement your strategy in your fluid, in the fluid or in the waves that apply it into the elastic waves, because many of the techniques, I believe, can be used if you choose the correct material. So the second half of the talk will be an introduction of the proof of the low regularity local well-posedness. There is a huge machinery that you can run once you have the correct structure, especially for the multi-wave speed systems, including the system that we want to discuss today. Okay, so let me start with introducing the standard elastic waves. So there are many ways to derive the elastic wave equations from very beginning, but usually you will start from the position and the displacement. So P is the position, and you can define the deformation gradient to be, just the gradient of the P. You can consider the displacement instead of position because usually it will give a smaller solution, especially when you want to consider the small data regime. So U will be our fundamental unknowns of our PD. And there are many choices of stress tensor. So physically, you will start with strain tensor. Strain tensor is how the material getting stretched or deformed. And for each material, there is a specific, unique relation between stress and strain. Okay, so And the strain and the stress, you have many choice of stress tensor. I picked the so-called first Piola-Kirchhoff stress tensor just because it's very simple. Because when you take the divergence, you will have the two time derivative of the displacement. Okay. So you will see here, if you expand the expression of this divergence of the stress tensor, you will see you will have a quasi-linear wave equation where it's linear in terms of the second derivative of u, and the coefficient depends on the first derivative. Usually, you should think this c of du is some smooth function in terms of du. Okay, so this is a system. Now, in terms of the choice of the stress tensor, so let's look at equation 4. So if you remove this part, this matrix G tilde Ij, you will have the linear Hookean material. So when you take when you plug it into the elastic wave equation, you will get a standard linear elastic wave equation, which is 5 with the right-hand side to be 0. So this G corresponding to this G tilde. Okay. So if you are in 1D, the left-hand side of 5 is the simplest 1 plus 1D wave equation, which I prefer to use that in my introduction to my undergrad PDE course. Which describe the solution obeys the Hooke's law, which first discovered in the 1600s, way before the first PDE ever written out. So if you consider the full matrix G tilde in terms of the deformation gradient, it's very complicated. So I will slightly peel the different types of materials and let you know the difference in between those materials. So in our work, we consider the case when the first matrix is actually a function of deformation gradient times the identity matrix. And I will let you know why we choose this stress tensor and why we cannot extend our result to a larger subset of the elastic materials. Okay, so as you can see, the choice at this point there is no Lagrangian introduced. So actually, it's quite different from other systems. So for elastic wave systems, there is not necessarily it's not necessary to introduce a Lagrangian based on how the material is like. So let me give you an example. So if you D-shape the material in different ways, you may result have different energies. So for example, if I press the material left and right and stretch it up and down, compared to I stretch it up and down first, then press it left and right, you may have, although the starting state and the ending state are the same, but the change of the energy may be different. So in that case, there is no chance that you can write a Lagrangian. In the case that the D-shape does not care about the order or the trajectory of how you D-shape, that's called a hyperelastic material, which is not necessary that we want to use, but it is being used in many previous works, so I think it's worth my while to mention it. So, so suppose the material has hyperelasticity. That means you can have an energy store functional or potential function W depend on the deformation gradient, so that the stress tensor can be expressed as a derivative of W over derivative of F. Okay, so think about the rubber, which is kind of an approximation to an ideal hyperelastic material. Okay, so moreover, if your material is isotropic, which means it's immune to the rotation, you can write your energy store functional to be a function depends on FF transpose. And this FF transpose is called Cauchy-Green strain tensor. And in this regime, you can write this Lagrangian. and you can take Euler-Lagrangian equation, which will get the same form as what you have for the elastic wave equation shown in the previous slides. Okay, so those were generic setup. So I just want to mention our choice of stress tensor may not even be hyperelastic. That's the point I want to make. Okay, so now we can finally get rid of the physics part and move to the PDE part. So the first thing I want to do is the standard local well-posedness. Okay, I will tell you very soon what do I mean by standard. So I run the energy method. Okay, so I rewrite the elastic wave equation into an operator act on U. And I pick this capital U, capital Q and a little q, which is some combination of the first derivative of V. Okay, V will be the candidate of the derivative of U for you to finish the energy estimates. So it's nothing special, but multiplying your elastic wave equation by dt of V. Okay. So you do the divergence theorem, and by the cohesiveness of Q0, you will reach the very standard energy estimates like you see every day in fluids and in the wave. Okay, so that tells you Hn norm of U can be bounded by the Hn norm of U at the initial layer plus the integral term. And this is the main term that you want to control. So it's so this is a term that you are going to ground wall, if naively speaking. So if you ground wall this integration term, you want to understand or you want to control L infinity in X, L1 in time for this second derivative of U. Okay, so the main idea of low regularity, local well-posedness is super simple. It is just to control this guy, okay, in L infinity normal of X and one normal in time. It's very simple, but things becomes complicated when n is below 3.5. So everything is fine above 3.5 because when n is greater than 3.5, you can recover this guy by Sobolev embedding. Okay, you can make a bootstrap assumption on the boundedness of this guy, and you can recover it by Sobolev embedding. Okay, so everything above H 3.5 is the classical regime that we talk about. So you can finish your proof of local well-posedness by just implementing energy estimates plus the Sobolev embedding. Okay. So when I talk about the low regularity regime, the upper bound is 3.5. So everything below H 3.5 can be considered low regularity. And there is a natural lower bound. So the scale critical level is H 2.5. Okay, so you shouldn't expect to prove anything beautiful in the critical level. So actually, the domain of low regularity is in between H 2.5 plus and H 3.5. Okay. So the controlling of this term will be the main part of understanding the whole problem. It seems a very simple task, but it turns out it's super complicated and it involves the geometry of the dynamics at some point.
Can I interrupt?
Yeah.
You really only need this term to be integrable in time, right? It can blow up.
Yeah. Itself can be blow up.
Yeah.
Yeah.
That's okay.
Yeah. So you want the mixed norm to be bounded. Yeah. Okay. So we talk about the low regularity regime between H 2.5 and H 3.5. And there is another natural barrier, which is the shock formation. Okay. So there is an Well-posedness driven by the instantaneous shock formation if U is in H3. Okay, to be more specific, pick our material. You can have divergence part to live in H3 and the curl part to be smooth, and you can still have this instantaneous shock formation. So that's really physical because it's just telling you it's the pressure wave that gives you the shock. Okay, so I will mention this result later on because there is still an open problem whether you can find some material so that you can go below H3. So this H3 Well-posedness is for generic elastic materials. Okay, so I will mention that later on more. So, so our result is want to prove the divergence part in H3 plus and the curl part in H4 plus. So which will connect well with this Well-posedness result, because this Well-posedness result can allow even smooth curl part. Okay, so I want to mention.
Sorry, this result by Chen and Yin, that's not irrotation.
Yeah, it's not irrotational. So it's assuming the H3 for divergence part and the smooth curl part. Yeah. So in terms of irrotationality, there is a discussion. So it's unlike the Euler, the irrotationality may not be conserved or preserved by the solution. So we will mention that later. It's very subtle. So a beautiful result I want to mention is by Lars Anderson and Lev Kompetansky. They proved the low regularity, low well-posedness for the incompressible neo-Hookean material. So we are using a very different approach to this, but I want to mention this result because they rewrite the elastic wave system into a fluid equation. Okay, so because they are working on an incompressible regime, so the equation that they derive is very similar to incompressible Euler, except that they have 4 velocity vector fields. So in total, 12 velocity components. So one velocity vector field is the real velocity, and the other 3 was the fake velocity, which come from the deformation gradient. Okay, so that's the low regularity result so far. And I also want to mention some long time result because by self-rescaling, there is a connection between the long time small data result and the short time large data result. Okay, so it really depends on the structure of your material. If you have null condition, you can prove the global existence. And if not, you can have almost global existence. And you can also have the singular, and you also have the finite shock formation. Those results, I believe, was done by Fritz John in 1D. Okay. So I want to explain why the techniques in the long time result with small data is not helpful for our problem. So first of all, in terms of the long time result, long time small data result, they consider the truncated elastic wave equations. So they only consider nonlinearity up to quadratic. So they only consider the nonlinearity up to du times d squared u. Okay, not like, so they just drop off the terms like du squared times d squared u. Because in their regime, they consider small data, so du is small. So adding more nonlinearity will not harm the system, so they can just drop those terms out. Just drop those terms off. But for the local well-posedness, when you have large data, when du is really large, these terms cannot be dropped. So we need to consider the full elastic wave system instead of the truncated version. So the next difficulty that we have here is in the long time result, usually you will run L infinity, L2 decay estimates and close and get the long time or global existence. And that techniques usually requires 5 to 10 derivatives. And we are only allowed to take 3 derivatives in L2. Okay, so we are left with 2 choices. The first choice is understanding the quasi-linear wave system, which basically people knows little about this system. The other choice is to try to use the knowledge for one quasi-linear wave equations and find a good structure for both the divergence part and the curl part. Okay, so I'm convinced you that it's a multi-speed problem by simply taking the divergence and the curl naively. So if you ignore the right-hand side, you will receive 2 wave equations with different speed. Usually C1 is greater than C2. Just a physical phenomena that longitudinal pressure wave is traveling faster than the shear wave. So everything will be fine if the data is small, but if the size of du is large, then the divergence part may not represent the faster wave. That will cause a huge issue. Okay, so this is the place that we want to avoid. But at least for now, we know that the system that we get is a multi-speed problem, and it related to quasi-linear wave equations. Okay, that's the two information that we got so far. So I want to start with introducing the low regularity results for quasi-linear wave equations. There are two types of it. So this is the first type when the Lorentzian metric G depends on the solution itself. In the next page, the G depends on the first derivative of the solution. Okay. So the standard level is H2.5. And the scale critical level is H1.5. So the first breakthrough into the low regularity regime is in late 90s when Bahari Shaman and Tataru used streetcar estimates, which I will mention more on this topic, to go below H2.5. And it was improved by Tataru to loss of 1/6. Okay, this 1/6 is claimed to be really sharp if you only play around the streetcar estimates. But there is if you want to go below, you need something fantastic. So Kleinemann and Ronowski make those observation that no longer, not only the solution phi itself satisfy the wave equation, but also the metric G satisfy the wave equation. And the right-hand side gives you the Ricci curvature of the metric. This idea was traced back to the 1950s when Madden, Choquet, Bruhat first derived the local well-posedness for Einstein vacuum equation using wave gauge. So the good thing about that is once you have the box G equals to Ricci of G, then you can gain regularity for your Ricci coverage, which will be very important in the whole analysis. I will talk about a little bit in the proof session. So with this observation, the optimal result was derived by Smith-Tataru using a paradifferential approach and by Chen Wang in 17 using the vector field method approach. And you will have the H2 Well-posedness driven by the instantaneous shock formation at the level of H2. And for the system that shock is not present, you can even go lower. So for the Einstein vacuum equations, you can prove H2. H2 means H2 for metric, so it's L2 for the curvature. And whether this H2 is optimal for Einstein vacuum equation is still open. Okay, it's considered to be a very hard problem. Okay, so that's the first type of the quasi-linear wave. So the second quasi-linear wave is just G depends on the derivative of phi. So there is an easy trick that you differentiate the equation and you change the variable d phi to phi, and you will go back to the first type. So many results can be put here. Many results before can be put here. So classical result is apparently H3.5, and scale critical is H2.5, and Smith, Tataru, and Wang's result is H3 plus now. Okay, so the elastic wave equation is at the form of this. So this is actually the model that we are interested in. So there is a very special thing for this type of quasi-linear wave. If you have very good nonlinearity, you can go below H3. So there is some models that verify 17 that has no shock. Okay, in that case, you can go below H3. So the work by R. Ephraim Tataru and Moschidis Ronowski, they consider the time-like minimal surface equation, and they can go below H3. So this is like H3 minus 1/4, and this is H3 minus 1/3. Whether can people find such structure in the elastic wave is unknown. So this is another interesting open question in terms of the elastic wave equations. Okay. So the optimal level was conjectured to be H2.5 plus, just because this is the scale critical level. Okay. So that's the quasi-linear wave equations with single speed. There is no multi-speed introduced. but we know the elastic wave has multi-speed. So I want to give you an important example of a multi-speed system, which is the compressible Euler. Okay, so if you want to prove low regularity local well-posedness result for a multi-speed problem, you need, as for the current techniques, you need two things. The first thing is that you want to have regularity gain on both sides. So take an example of compressible Euler. The velocity satisfies the wave equation, and so does the density. I just too lazy to write density equation out. So velocity satisfies the wave equation. Everything else is good except the vorticity or vorticity. This term is really bad, but it can be saved by the transport equation. The material derivative act on the vorticity or vorticity gives you derivative of vorticity times derivative of velocity. Okay, so so by counting the derivatives, you know that when you apply the transport estimates, the vorticity of vorticity, well, I should say derivative of vorticity because the divergence of vorticity is trivial. The derivative of vorticity depends on partial v, right? Because this term you will wrong void. There is nothing worried about it. So you have a pretty good regularity gain because the partial omega depends on partial v. Now you can replace this partial omega here, right? So the vorticity omega is actually partial v. So you can close the estimates for both. So it's a miracle in a compressible Euler in terms of the regularity gain. So that's the first part. You want to have regularity gain on both sides, especially you want to have some huge regularity gain on the slower wave side. So, and also one feature in compressible Euler, which is quite natural, is that the transport part is strictly slower than the wave part. It's like the fluid is moving, of course, slower than the fluid plus the sound, right? So that's the first good feature. The second good feature is certain decoupling exists. Okay, so for compressible Euler equations, it is well known that if initially the system is irrotational and isentropic, it will remain irrotational and isentropic until the shock forms, right? So this secretly tells you there are some decoupling properties that the wave part will not affect the transport part too much in the compressible Euler system. Okay, so unfortunately, the generic elastic wave equation does not satisfy either of this. So we want to investigate a subset of elastic wave equations, and hopefully we can get the similar properties. That's the goal. So in terms of the compressible Euler equations, an interesting phenomena, which is kind of weird. Okay, so let me explain it carefully. So again, the classical level is H2.5. Once you want to lower the wave part from H2.5 to H2, you will increase the curl part. Okay, so this H2 plus is for the vorticity. So it's like H3 plus for the curl part. So the idea is if you want to lower the regularity assumption for wave part, you need to increase the regularity assumption for the transport part. Okay, so H2 plus for velocity and H2 plus for vorticity. This is very natural if you look at the equation 18a, right? Although you can gain this vorticity or vorticity regularity back, but you still need a higher assumption for your vorticity part. You need a one regularity high, 1 degree higher for your vorticity, right? So that's a common feature for the compressible Euler, and you also see that in elastic wave in the main theorem that we impose H3 plus for the divergence part and H4 plus for the curl part, exactly for the same reason. Okay. So there is a parallel development also in the relativistic Euler equations, which is basically the same result, just slightly different equation structures. Okay, so now we want to ask one thing, that can we find some decoupling property for elastic wave equations, just like what we did for Euler, such that if initially there is no vorticity, there will be no vorticity afterwards? The answer is yes, you can classify it, and the people call it harmonic. The material is harmonic if and only if the pseudo-irrotationality is preserved. Okay, so the harmonic material was used a lot in the engineering. So in engineering, they have a harmonic material, then they can just induce the pressure wave, and they can get rid of the shear wave and do the analysis that they want. So there is surprisingly good result of how you can classify the harmonic elastomer materials by Fritz-John in 1960s. So this is a very strong condition. It's an if and only if condition. So the material, okay, so let me be careful. So if you restrict yourself into the hyperelastic isotropic material, then this is an if and only if condition. So the material being harmonic, if and only if this function W depends on an arbitrary function of R plus AS plus BT. So AB are constants and R, ST are principal invariants of the root of the Cauchy-Green strain tensor. Okay. So under the regime of harmonic material, the elastic wave behaves much like the compressible Euler, but not yet. It is actually worse than a compressible Euler. So we know that if there is no vorticity initially, there will be no vorticity afterwards. But what if there is vorticity initially? Then we don't anything. We don't know anything, or at least for now. So because the curl part does not satisfy the wave equation, it is actually still a wave system, and we know nothing about it. That's the unfortunate part. Hopefully one day we can understand the whole regime of the harmonic material. So that's why we choose to consider this so-called admissible harmonic elastic material. So in the regime that is hyperelastic and isotropic, the material that we consider is actually a subset of the harmonic material. So the good thing about this stress tensor is that after you take the divergence of the stress tensor, the second term will become more like a trivial zero. The first term will be like a gradient of something. So when you take the curl, the whole term is going away. So what you left is a beautiful structure when the curl part is decoupled from the system. Okay, although you still lose derivative for the curl part in the wave equation. So if you plug in the stress tensor into the elastic wave equation, this is the system that you will get. So for the divergence part, this is a quasi-linear wave, but you have lost derivative in terms of the curl part, just like what you have for the compressible Euler. And for the curl part, it's fully decoupled. Okay, so in our case, it's actually a linear wave equation, but as long as it's fully decoupled, we understand how to solve it. So there is no phi in the system, okay, which is very important. So that we don't have miracle structure that gain you multiple derivatives of divergence part in the wave in the curl equation, but the equation is fully decoupled. That means you can run the machinery of streetcards estimates and so on and so forth. Run the machinery of low regularity local well-posedness. So, so if you write, so if you draw the picture of the wave propagation, you will have the divergence part is strictly traveled faster than the curl part. And this is the machinery that I talk about for solving for constructing the local well-posedness in the low regularity regime. So the colored box is the new ingredient needed for the elastic wave system. And the uncolored box, like the conformal energy estimates and the streetcards estimates, they are well established, although it's very tedious but it's well constructed for the quasi-linear wave equations. For those guys who are not super familiar with those methods, I will go through a little bit. So let me start with the very standard streetcards estimates in the textbook. So it was first used to understand the linear equation in 70s. So basically, you can have this estimate for in terms of the norms of derivative of the solution. Well, you can play with Strickard's pair. There are two pairs that are very important. One pair is the pair where rho PQ equals to 0, infinity 2. That's the energy estimates. Okay, so that's one pair which is important. The other pair is when this less equality becomes equality. When this becomes equality, this is so-called endpoint Strickards. And the rest of the Strickards estimates can be derived by the interpolation between the energy estimates and endpoint Strickards. Okay, so I want to mention there is one point forbidden where n is 3 is unfortunately exactly the estimates that we want. Okay, so it's 1 to infinity. So as I mentioned, you want to control actually for the wave equation, you want to understand the term that is groundward is actually the L infinity norm in X, L1 norm in time of partial G. Okay, so this is exactly what we want. So that's the linear level. So what about the quasi-linear wave equation? Well, everything is fine above C2. That's well understood in the 90s. And there is a counterexample when the Strickard estimates fail when G is below C2. It's terrible because our G is in H2 plus. Okay, that's a terrible news. So how do people overcome it? The key idea is to not do the sharp Strickard estimates, but pay a little bit of price. So what do I mean by that? So this is the Strickard estimate, estimate 28. So you don't prove the exact Strickard estimates, but you pay a price, you lose a little bit. Instead of L2 here, you write it as H delta. So you lose delta regularity. Okay, so that you can ignore the low regularity of G. Okay. So the first result by Bohari, Shaman, and Tataru, the loss is 1/4. So instead of L2 here and here, you have H1/4. Okay. So if you play with those indices, there is a maximum loss. There is a minimal loss they can have is 1/6. That's how Tataru improved the result to H2 plus 1/6 for quasi-linear wave. Okay. So, so if you want to go below, then the 1/6 above the shock level, you want to reduce the 1/6 to epsilon. You want to run a more delicate estimates, which involves the introduction of the geometry, which is the most interesting part, I think, for the whole problem. So, so let's ignore the Littlewood-Paley part. This is mainly used to prove the first part. The first part is you can think this is the derivative of G in L2T, L infinity X. Okay, so this is the bootstrap assumption, and you will improve the one on the right-hand side by time. Because time is small, so this is a strict improvement because you only prove a local result. So you rescale it so that you want to prove a decay over time, over quite a long time. You rescale it in terms of the frequency. So you have P nu here, but you have P1 here. So you rescale it over nu, and the time slab increase by nu. Okay, so the precise structure here is not super important. So the thing is, you want to prove the decay estimates for this linearized wave equation. So this phi and this phi are different. Okay. So it is well known that the tangential derivatives of the solution decays faster than the transversal derivative of the solution for wave equations. So you want to distinguish that. So let's draw a null cone. L and EAEB are tangent to this null cone or null or characteristics of the Lorentzian metric G. And this cone is prescribed by the level set of u. U is constant along the cone. And L bar is the transversal direction. Okay, so if you run the decay estimates, so in our work, we don't run the Morawitz decay estimates, but I feel like it's very convenient to show you what's going on if you run the decay estimates like this. You will distinguish the bad terms, just like this. So if you run the Morawitz estimates, the energy that you hope to control is like this. So you can see U is like T minus X, U bar is like T plus X. So you can see the transversal derivative decay is much worse than the tangential derivatives, right? It's 1 over T minus X. Okay, so that's the thing that we hope to control. And to control this, we need to control the bulk term. Q is the energy momentum tensor, and the pi is the deformation gradient, deformation tensor, which depends on the first derivative of the metric. Okay, so the worst term in this bulk will be like this. Okay, so trace chi is the expansion scalar, which tells you how fast the cone is growing. The worst term is like this because trace chi minus 2 over r is like 1 over t squared. And unfortunately, you have L phi, which is okay, but you have L bar phi, which is not okay. So this term, you cannot conclude this term, you cannot bound this term by the energy. Okay, so that's when the geometry plays in. Okay, this is the interesting part. What you want to do is you integration by part for the L bar phi. So L bar phi falls on trace chi. L bar phi falls on L phi, which then you replace it by the wave equation. Okay, when you replace it by wave equation, you will have angular Laplacian phi times phi, and then you do the integration by part again. So you pick up angular trace chi times this term plus the trace chi times angular phi squared. Okay, so you apply integration by parts twice so that the phi has good decay now. The phi has good decay now. There is no transversal derivative, so phi, but you pay the price that you take another derivative of the connection coefficients, which is very bad because you have limited regularity for the metric. Okay. So the main task is to understand trace chi, especially in the L bar direction and angular direction. Okay, that's when the geometric equation comes in, which originated from the techniques in general relativity. So this is the famous Ricciardo equation, which is the transport equation satisfied by the trace chi. So if you take the L direction along the null cone of trace chi, you will pick up a Ricci curvature. And now you plug in the observation by Kleiman-Roniansky, which tells you the Ricci curvature is actually the box G of G. Okay, so secretly you gain one derivative. So let me explain how. So here, when you construct null frame, U is at the same level of G. Okay, so L and the null frame is like one derivative of G. Okay, based on this construction of null frame, all the vector fields are like one derivative of G. So the connection coefficients is like two derivatives, which is quite bad because the Ricci curvature is three derivatives. So you can gain one derivative back by plugging this observation. So you know that Ricci is actually the two derivatives of G. Okay. So that will recover the loss that you used during the construction of null frame. Okay. So something particular interesting is for the elastic wave is the slower speed component also come into play, and you have to carefully treat them because this psi does not satisfy a good equation. You have to just deal with it. You should think this is a three derivative of psi. That's another reason that you need the 1 degree higher of regularity assumption on the curl part. Okay, so so another thing subtle in the quasi in this setup is you have another top order term which is d gamma. So the goal is when you consider Ricci LL, you have L of gamma L. Gamma is the contracted Christoffel symbol. When you have L of gamma L, you just soak this term to the left. Okay. So what you are trying to control is not trace chi, but the trace chi minus gamma L, which is first used in Wang's work for the low regularity local well-posedness for quasi-linear wave equations. So maybe I should go back to here and tell you the story of how you control the L bar trace chi and angular trace chi. It's very simple. You just commute this equation with L bar and angular derivative, and you will have two nasty terms. First is the mass aspect function, okay, which help you to understand this L bar trace chi. This was first shown in the Christodoulou-Kleinman's work on the stability of Minkowski spacetime. And the other nasty term is the angular trace chi. So the angular trace chi was tackled by conformally change the metric so that you, instead of considering trace chi, you consider this trace chi tilde, which is trace chi plus gamma L. Then you have a good, you have kind of like renormalized the Ricci-Derry equation so that you can run the estimates without any. Okay, so the difficulty exclusively for the elastic wave equation come into two folds. The first one is you want to show that the slow wave part is always the slow wave part. Okay, so this is not 100% trivial. First, you need to make a hyperbolicity assumptions so that initially it's hyperbolic. Initially, the faster wave part is the faster wave. But secondly, you need to control all the quantities so that this distinguish does not disappear after a short time. The second difficulty is when G depends on the slower wave part. So G is the metric for the faster wave characteristics. But it also depends on the slower wave. So that will give some problems because the connection coefficients and the second fundamental form will depend on the two derivative of psi. So I use capital psi here. So so this is the below top order, but you also have the top order, which is when you use the box G of G, because box G of psi is not a good equation because psi satisfies the other wave equation. So this is bad. This comes into the top order play. And this term appears everywhere in the Ricci curvature. So basically it's everywhere in your system when you try to estimate, when you try to do the Kohn energy estimates. Okay, so, but luckily the curl part is fully decoupled from the system. So it's okay that you lose derivatives here because you can always gain back from the decoupled system. So, so before I sign off, I should talk about future interests. So the first thing I want to understand, hopefully, is understand a large subset of elastic wave equations. So in particular, I really want to know if there is an elastic material so that you can go below the regularity level of H3, right? So can you find the elastic wave equation that has no shock? Maybe that's the first task. And the other thing that should be interesting is, can you prove local well-posedness in low regularity regime for all the harmonic elastic material, but not a subset of it? Okay, so the next part is the optimal result for the curl part. This is also an big open problem for the compressible Euler. So for compressible Euler, the current best result is H2 plus for velocity and H2 plus for vorticity. The conjecture for vorticity is H1.5 plus because it matches the it matches the regularity level for the incompressible oil. Okay, but it's not necessarily true. So people not sure about the optimal level for the vorticity for the compressible oil, and same for the elastic wave system. So our assumption is H3 plus for divergence part and H4 plus for curl part. There is a chance that you don't need H4. Okay. So another interesting topic is the description of long-time behavior of elastic wave equations without null conditions. So there are some shock-forming results in 1D, but it's done 30, 40 years ago. So there definitely is something to be investigated into if you want to construct the finite time blow up. So in particular for harmonic elastic material, if there is no vorticity initially, the system becomes a quasi-linear wave equation. So it's very easy for you to construct shock by imposing different data for the divergence part. Okay, so so you can have investigate into other multi-wave speed systems. For example, MHD, which I think is much harder than the elastic wave because you don't have choices to choose your material, and you have to deal with the triple speed system. You have 2 wave speed and 1 transport speed. So I think I should conclude my talk here, and looking forward to your questions.